In this module, you will discover how the pressure in the water varies, learn the necessary equalization techniques so as to avoid pressure imbalances, find out how the buoyancy varies with the depth, and you will also learn how to communicate when freediving. Air and water. The world we live in is a physical, tangible reality. As such, everything that belongs to you has a substance, meaning it is made up of real elements. These elements in our very tiny world are called molecules. The combination of all the molecules that make up a single individual or body is its mass. Every person therefore has his or her own mass. The larger a person is, the greater the mass. More molecules are needed to make it. There are other properties that do not belong to everything that surrounds us. A solid, for example, a stone, has a mass and occupies a well-determined amount of space, called volume. What is more, a solid also has its own shape. For example, the stone can be a sphere, or in the case of a brick, a parallelepiped or cube, although in general its shape will be irregular. If we take a liquid, for example water, we immediately discover that although it has mass and volume measured in litres, it does not have its own shape, but assumes that of the container it is in. Gases like air have only mass and have neither their own shape nor volume. Let's verify this. Take a syringe for hypodermic injections and removing the needle, draw air into it. Now let's close the exit hole well and press on the plunger. We discover that by increasing the pressure applied to the plunger, we can reduce the volume of air in the syringe. We are compressing the air. Let's now repeat the same experiment, but this time drawing water into the syringe. However hard we push, we cannot compress the water. We have therefore directly verified an important property of gases. They are compressible, unlike liquids that are practically incompressible. Pressure, depth and volume. In the previous chapter, you learned that an essential feature of the mask is that it incorporates the nose so that it can be pinched closed from the outside. These features of the mask derive from an extremely important phenomenon for us freedivers: the increase in pressure with depth. But what is pressure? In physical terms, pressure is the force acting on a surface. Think, for example, of our planet. Wherever you are, there is air around you. Due to the force of gravity, the air molecules are attracted downwards. That is, they have a weight. This means that every layer of molecules supports the weight of all those above. The weight of the air above bears down evenly and in all directions on the bodies pushing on their surface. This push is called atmospheric pressure. At sea level, the atmospheric pressure is worth 1013 hectopascals. For simplicity, however, we will continue to use the old unit of measurement of 1 atm, atmosphere. If you climb up a mountain to 3,000 meters above sea level, the weight of the overlying molecules of the layer of air where you are is less. At that altitude, the atmospheric pressure is lower than it is at sea level and is about 0.7 atm. In water, changes in pressure happen very quickly and involve quite unusual situations and procedures. pressure in saltwater increases linearly with the depth. It increases by roughly 0.1 atm every meter. To create a pressure of 1 atm, like that originating at sea level from all the Earth's atmosphere, a column of saltwater just 10 meters high is sufficient. The pressure generated by the water is called hydrostatic. We divers, on the other hand, are interested in measuring the total pressure at the depth we are at. We will therefore use the absolute pressure, which is the sum of the hydrostatic plus the atmospheric. At 10 meters of depth, you are already at a pressure that is 1 atm higher than that on the surface. That is at an absolute pressure of 2 ATA. While on reaching 20 meters, you will have 2 atm more, meaning an absolute pressure of 3 ATA. Diving under the water, the increase in hydrostatic pressure is immediately perceptible to the tympanic membranes. It is not easy to perceive pressure changes in the rest of the body, as it is made up of solids and liquids that, in practice, reach the new pressure without any variation in volume. The parts of our body that can be affected by the phenomenon of compression are the gaseous cavities. If we took a balloon full of gas under the water, we would immediately see that as it goes down, its volume is reduced. The volume change in the balloon is inversely proportional to the absolute pressure. This means that if the absolute pressure doubles, the volume of the gas halves. If the absolute pressure triples, the volume becomes a third. To understand the effects of pressure on the body, we also need to consider whether a cavity is connected with the outside of the body directly or through a membrane. If you take a bucket under the water, keeping the opening downwards, the increase in pressure causes a reduction in the volume of air, with the water entering the bucket. If instead you descend with the bucket closed with the plastic membrane, the force of the hydrostatic pressure will curve the plastic film towards the inside of the bucket, introflexion, to try to equalize the internal pressure with the external one. As you descend further, the membrane stretches to the maximum, resisting the action of hydrostatic pressure. Inside the cavity, the pressure is lower than that outside. We are therefore in a situation of baric imbalance in compression. Because the pressures are different inside and outside the cavity, and this inequality has occurred during the descent, that is, in compression. This situation can only last until the membrane, now stretched too tightly, breaks due to the still increasing pressure. In order to avoid pressure imbalance, you have to find a way to emit gas into the cavity, equalizing the internal pressure with the external one. This operation is called equalization. Equalization. The parts of our body affected by the compression of the gases during the dive are mainly the internal cavities connected to the respiratory system. These cavities which contain air are affected by this physical phenomenon. While for the lungs, the phenomenon of reduction of the volume of gases during a dive triggers an automatic compensation mechanism called blood shift, which will be dealt with later. As regards the middle ear, it is necessary to act using equalization maneuvers aimed at rebalancing the tympanic membrane, which is pushed by the hydrostatic pressure towards the inside of the ear. The ear is divided into three parts: the outer ear, a simple open cavity that does not require equalization; the middle ear, a gaseous cavity separated from the outside by a membrane called the tympanum; the inner ear, composed of solid and liquid materials and therefore incompressible. The middle ear is the part subject through the eardrum to the phenomenon of the compression of gases. As you dive deeper, the pressure increases, the eardrum introflexes, and if it is stretched too much, gives rise to a fastidious sense of compression, which turns into pain as the descent continues. Continuing the descent even further can cause the tympanum to rupture. Fortunately for us, the middle ear is connected to the mouth through a small duct, the auditory tube, also known as the eustachian tube. With some special maneuvers called equalization, we can emit air into the middle ear from the throat to compensate for the external pressure. The eustachian tube is normally closed to prevent bacteria from entering the middle ear. To open it, it is necessary for most of us to create a slight overpressure in the nose. Generally, this is done by performing the Valsalva maneuver. You pinch your nose with your fingers and gently blow into your nose. However, the Valsalva maneuver, widely used in scuba diving, is not efficient for freediving. For a freediver, it is particularly difficult to use the abdominal muscles to push the air downwards from the lungs to the middle ear, creating the overpressure needed to compensate for the pressure difference. In general, freedivers prefer the Frenzel or Marcante Odalia maneuver. You pinch your nose, close your mouth using your tongue, and lightly press the tongue towards the throat. Your PSS instructor will show you practically the techniques you need to use so as to implement effective equalization. With this action, we equalize the pressure not only in the middle ear, but thanks to internal ducts, also in a series of gaseous cavities of the skull called the paranasal sinuses. We recommend that you do not dive when you have severe sinusitis or a bad cold. In fact, in these conditions, the occlusion of the paranasal sinuses or eustachian tubes can prevent you from performing the equalization maneuver, and not being able to equalize means that making a freedive becomes impossible. If during a descent you feel a sense of painful pressure in your ears and you can't equalize, you must stop and ascend. You can make other attempts trying during the descent to equalize continuously, but gently. If you do not manage to equalize, it is useless to force it, and for that day you have to abandon the freediving excursion. We also have artificial cavities separated from the outside by a membrane. One of these is precisely the air cushion enclosed in the mask. As the mask skirt is soft, this air cushion reduces in volume under the effect of the increasing pressure. However, when the mask is no longer able to deform, for example, because the rigid frame is pushing on the nose, the pressure inside is lower than the external one. If the difference is great, the ocular capillaries can break, resulting in the leakage of blood, which makes the eye red. Avoiding this effect, called mask squeeze, is in any case very easy. Just blow a little bit of air through the nose into the mask during the descent. Blood shift. Thoracic hemocompensation. In the past, it was believed that lung volume limited the depth of a freedive. It was thought, in fact, that when the volume of the air contained in the lungs and in the dead air spaces was reduced, with the increase in pressure to just the residual volume, that is the irreducible part, every further metre of descent would have caused the lungs to be crushed. Doctors and researchers ruled that after taking a breath on the surface, the maximum depth that could be reached on a dive without causing damage was between 30 and 40 meters. The depth of 30 meters was already exceeded in 1949 by Raimondo Buccia. Two other Italians, Ennio Falco and Alberto Novelli, reached the depth of 41 meters in 1956. How is it possible? Thanks to a phenomenon called blood shift, thoracic hemocompensation. In fact, as the pressure increases, our body reacts by limiting the mass of blood circulating in the peripheral areas and increases that in the ribcage. Blood is liquid, therefore incompressible, so it occupies part of the residual volume, allowing the air in the lungs to compress further without crushing of the ribcage. This phenomenon is linked to other reactions that occur in the cardiovascular and respiratory system. When a mammal immerses its face in water, a phenomenon called the diving reflex or diving response, which we will discuss later. Pressure imbalances on ascent. Your lungs are a gaseous cavity which may be in communication with the outside, open glottis, or not, closed glottis. If you free dive and keep your mouth glottis closed for the whole dive, you have no problem. But if on the bottom you breathe air from scuba diving equipment and then ascend while holding your breath, this will cause an imbalance of pressure in the lungs in the decompression stage. In fact, breathing air at depth, you take more air into your lungs, adding to that you already descended with. During the ascent, the air expands, reaching a volume well above that which can be contained in your lungs. The increased volume of expanding air will rupture the delicate lung structure with very serious consequences. When freediving, you must never breathe from scuba diving equipment. Buoyancy. As Archimedes discovered, any object immersed in a liquid receives a thrust upwards equal to the weight of the liquid displaced. This force, called hydrostatic thrust, therefore opposes the weight of the object. Imagine taking a plastic bottle for mineral water with an external volume of 1 litre. When it is completely immersed in water, it displaces 1 litre of water. Since a litre of fresh water weighs 1 kilogram, according to Archimedes' principle, the hydrostatic thrust towards the surface will be exactly 1 kilogram. What happens to the bottle? It depends on what it contains. If you filled it with an element heavier than water, it will weigh more than 1 kilogram. The weight is greater than the hydrostatic thrust, and the bottle will start to sink to the bottom. This condition is defined as negative buoyancy. If you have filled the bottle with water, it will weigh 1 kilogram. So the hydrostatic thrust equals the weight exactly. This condition is called neutral buoyancy. The bottle can stay still at any depth. If instead the bottle is empty, that is full of air, it weighs just a few tens of grams and will therefore return to the surface immediately. This condition is called positive buoyancy. The variation in buoyancy is one of the most important factors which the freediver must learn to live with. Do not believe that it is easy to manage, because it goes from positive to negative during the dive with the increase in depth, and from negative to positive during the ascent. The pressure variation causes an inverse variation in volume, but varying the volume changes the quantity of liquid displaced, and consequently the buoyancy, while the weight stays the same. Ultimately, the condition of buoyancy varies. Let's take a practical example, the neoprene wetsuit. thousands of gas bubbles are enclosed within the neoprene foam. The bubbles are subject to the pressure increase at depth, and their volume is reduced. A practical consequence of this is that the thickness of the suit is reduced as you go deeper. At 10 meters, the absolute pressure is doubled and the volume of bubbles has been halved. This means that the volume of liquid displaced by the suit is almost halved. Almost, because the neoprene is incompressible. Therefore, the hydrostatic thrust decreases and buoyancy becomes negative. On the other hand, with a neoprene wetsuit, you assume a condition of very positive buoyancy on the surface. To descend without too much effort, you have to wear weights. The weight system. The weight system consists of a set of weights made of lead, which can be easily released and abandoned if it is necessary to assume greater buoyancy. For example, on the surface, if you get very tired. The traditional weight system is based on a nylon belt about 5 centimeters high, fitted with a metal or plastic end buckle. The weight belt buckle must be of a quick release type, which can be operated with just one hand. When scuba diving, it is positioned at the level of waist, so that with the reduction in the thickness of the wetsuit at depth, the belt does not slip down onto the hips. When freediving, the abdominal area around the waist must be free in order to allow effective diaphragmatic breathing. So the belt is positioned lower down on the hips. For this reason, freedivers prefer to use an elastic rubber belt. The elasticity of the rubber is able to compensate for the decrease in volume of the suit during the dive, allowing the belt to stay in place during the dive. Lead weights of different shapes and sizes from 0.5 to 2 kilograms each are threaded onto the belt, even if the ideal is to distribute the weight symmetrically using 1 kilogram weights. The belt should not be too long. You will certainly be wondering how many kilograms of weight you will need to use. It is impossible to calculate it first, as there are too many factors that affect the calculation. If you imagine making a free dive, you'll be able to understand how the buoyancy varies during the phases of the dive. On the surface, your buoyancy will be slightly positive, and you will have to overcome this with a pike dive so as to start the descent. During the descent, the pressure increases, compressing the air in the lungs and the gas bubbles in the wetsuit, and the thickness of the suit will decrease. The volume of the chest and the volume of the wetsuit are reduced. Ultimately, you displace less water, and your thrust towards the surface will decrease, with a consequent loss of buoyancy. At a certain depth, depending on the amount of weight used, you will find yourself in a neutral buoyancy zone. This depth is called the depth of neutral buoyancy, and you will neither be pushed upwards towards the surface nor downwards towards the bottom. Typically, you will have to adjust your weights so as to reach the condition of neutral buoyancy at around 10 meters of depth. During the ascent, the volume of air in the lungs and of gaseous bubbles in the wetsuit increases due to the reduction in the pressure, and thus giving you more and more buoyancy. However, your buoyancy will remain negative, and in order to ascend again, you will have to fin until you reach the depth of neutral buoyancy, around 10 meters. Of course, if your dives are limited to just a few meters deep, your depth of neutral buoyancy may vary. Your PSS instructor will explain how to determine the correct amount of weight. The density of the water in which you dive also influences the buoyancy. Salt water is denser, therefore heavier than fresh water. For the same amount of water displaced, in the sea you will receive a greater thrust than in a freshwater lake, so you will have greater buoyancy. To counteract the increased thrust of salt water, you need to add more weights to your weight belt. The difference is about 3% of your total weight, wearing full equipment, including weights. Remember to record the amount of weight you use for each dive excursion in a logbook, so it will be easier in the future to choose the right amount of weight in every situation. In any case, you must check the amount of weight at the beginning of every freediving excursion. Instrumentation. Thanks to the variation in pressure, it is possible to realize an instrument that is able to measure the depth. The depth gauge. Today, digital depth gauges are very common. They are real freediving computers that are able to give you a lot of useful information, such as time, temperature, and the data of the sequence of dives. The freediving computer allows you to set the recovery time on the surface between one dive and another, and to set a series of underwater alarms. Among these alarms, there is also a depth alarm. All these data should be set at the time of planning the freediving excursion, and in any case, before actually entering the water. Sound in water. Sound is a wave pressure. That is a very rapid increase in pressure which is transmitted from a molecule to those near it. In a vacuum, where there are no molecules, sound is not transmitted. In air, however, sound can be transmitted. However, each molecule must move closer to the others to raise the pressure, and as you already know, the molecules in gases are far apart. If instead the distance between them is small, as in the case in solids and liquids, to transmit the pressure wave, each molecule travels a shorter distance, but the total number of molecules to be moved is greater. This means that in water, sound propagates faster than it does in the air, but in order to be audible, it must have greater power. Our brain, even if at a conscious level we do not realize it, manages to distinguish the direction of origin of a sound in the air by analyzing the delay with which it reaches the two ears. Since sound travels about 4 times faster in water than it does in the air, this delay is so small that a noise always seems to come from in front of us, from whichever way we turn our heads. When you are just below the surface, be very careful if you hear the sound of a boat. Its dangerous propeller could be very close, but you will have difficulty in identifying the direction the sound is coming from. Communication systems. Since we cannot use the voice as a means of communication underwater, we are forced to invent different systems. But even on the surface, it is often not easy for a freediver to talk. If there are waves and you take the snorkel out of your mouth, you may inadvertently swallow water. For all these reasons, divers generally communicate using hand signals, which must be coded so as to be immediately understandable. Fortunately for us, the signals used by divers are practically the same all over the world and allow us to communicate simple concepts with divers from any country. However, it is not enough to give a signal. You need to be sure that your dive buddy has completely understood what we want to communicate. There are therefore precise procedures to be implemented. The first step is to get the attention of those who must receive the signal. Before giving a signal in the water, you must be sure that the person to whom it is addressed is actually looking at you. The signal must be simple, unambiguous, and previously agreed. Signals that are too complex are often not understood. There cannot be signals that are too similar, as they are ambiguous and could be misinterpreted by the recipient. Finally, there is no point in inventing a signal in the water. If it has not been agreed with the buddy before, it will be difficult to understand. To be sure that the communication has been effective, you must wait for the received signal. The best way to confirm you have understood what another diver wants to communicate is to repeat the signal and then give the OK sign. If you do not agree, you can answer no and repeat your signal. In this way, you indicate that you understand the request, but you do not agree with it. Naturally, for this communication system to be effective, it must be immediately understood by both dive buddies. So it is always best to review all the most important and specific general signals that you might need with your dive buddy before venturing into the water. Freedivers do not only communicate with each other in the water, but also with the person who takes care of the assistance on the boat or on the shore. You cannot always do this using your voice. The distance, the wind, rough seas can complicate communications. It is therefore necessary that the assistant also participates in the review of the general and specific signals. In the next module, you will discover all the freediver's secrets of respiration. You will learn the techniques of the buddy system, and you will understand the importance of having good physical fitness.